Hello, friends. Jim here. Welcome to Science Talk. In light of what's been going on, I thought this is a very prescient article to discuss with you. It appeared August 22nd, 2023, online publication of EOS. Landfast sea ice, the most important ice you've never heard of. Landfast sea ice is sea ice that is held stationary against the Antarctic continent, links firmly with many key climate processes, but its importance is only being fully realized as its extent dwindles. So let's see a bunch of cute little Adelie penguins doing what penguins do. Nice photo, I like it. Antarctic sea ice extent has plummeted throughout 2023. And keep in mind, they're in their winter coming out into eventually be their springtime. So they're losing their ice during their winter. That's extremely alarming. With its rapid loss surprising scientists across the world. That's like some 5, 6 standard deviations out of the norm. Meanwhile, attention is being drawn to the importance of landfast sea ice, sometimes called fast ice, which is locked in against and around the Antarctic coast. Fast ice is experiencing a decline of its own, as highlighted in a recent study in Reviews of Geophysics, which is bad news for the wide variety of Earth system processes linked to it. We asked some of the authors to give an overview of landfast ice, how scientists study it, and what is still not known. So, in simple terms, what is landfast ice and where does it occur? Landfast ice, confusingly abbreviated as fast ice, despite it's not moving, is sea ice, which has formed from the seawater freezing, but does not move in response to currents and winds, unlike pack ice. Fast ice can be fastened either to the coastline itself or commonly icebergs run aground on the relatively shallow Antarctic continental shelf at depths of up to about 400 meters. Generally, it forms a discontinuous belt around the Antarctic coastline with a width of 50 to 200 kilometers. Its area generally varies between about 221,000 and 601,000 square kilometers, so it forms a significant fraction of overall sea ice, about 3 to 19 million square kilometers. That's the overall sea ice. Excuse me. Why is it important to understand fast ice as distinct from other forms of sea ice? Fast ice has a variety of distinctly different roles in the physical, biogeochemical, and ecological systems when compared to pack ice. For example, due to its immobility, fast ice pushes mobile pack ice further to the north, thus contributing to the formation of polynyas. Polynyas, or regions of lower than expected ice concentration, are important for the global climate since they are regions of intensive heat transfer from the warm ocean, about minus 1.8 C, to the cold atmosphere. Polynyas generally tend to be open areas in the ice, and they're kind of basically biological oases, very important for marine life because there's no sea ice present to act as an insulator. Thus, polynyas are regions of very intensive sea ice production. As new ice forms, salt gets rejected back into the water because ice is fresher than the ocean, and therefore, it floats. This water that now contains the brine rejected, right? The brine rejection as salt is very dense and can sink, and therefore it helps in global ocean circulation, right? Thermohaline flow. You form the ice, you have brine rejection, so the water that remain becomes denser and it sinks. That's basically what they're saying. It's generally thicker than pack ice, acts as a reservoir of nutrients, for example, iron, which is important for phytoplankton, but in short supply. It serves a variety of ecological roles, acting as a crucial habitat for micrograzers, which all the way up to emperor penguins, which use the stable fast ice as wintertime breeding platform. That's an important point. Emperor penguins breed on ice. They don't go to the land, unlike Adelie or the some of the other smaller penguins species. And they're losing sea ice. This imperils emperor penguins. And when they refer to micrograzers, they're referring to bacteria, and other protists that ingest, some, of the nanoplankton and so on. Typically, those protists would be like amoeba-like uh, forms that can engulf the particle by forming a food vacuole, so on and so forth. What do we know about the formation, evolution, and decay of fast ice? We now have a satellite derived data set of 18 years of continuous observations of large scale Antarctica fast ice extent, 2000 to 2018. From this data set, we can determine the timing of fast ice formation, the maximum, the decay, and the minimum. However, the discrimination between pack and fast ice is still largely manual, i.e., requiring considerable time for a researcher to map the fast ice, thus reducing the objectivity of the maps. In other words, the satellite is not going to be able to distinguish between the two. You actually have to get in situ and make your observations. On a local scale, we have time series measurements of fast ice formation and decay from ice mass balance stations at a limited number of sites around the continent. However, these tend to be found in smooth fast ice, meaning that regions of rough fast ice, i.e., forming when pack ice becomes fastened due to onshore wind, are poorly understood. Well, also, the rough fast ice there, you have winds, you have ice rafting and folding of the ice, stuff like that. Scientific instrumentations do not really take too well to those kind of conditions. They're easily damaged. Where the smooth fast ice is kind of relatively stable, so they hold up better. Overall, fast ice observations are discontinuous, sparse, underdescribed. So here they have a little of fast ice anomalies from -1 to 1. So it's the distribution of anomalies in Antarctic fast ice extent in early to mid March 2022, based on the baseline from 2000 to 2021. A value of -1 indicates a lack of fast ice in 2022. Inset B is a time series of early to mid March fast ice extent from 2000 to 2022. Okay, and this is from Fraser and Wongpan et al. From 2023. So the inset shows fast ice extent in thousands of square kilometers, and thump, you can see it just dropped off in the last year or so. Been steady declining since about 2014, maybe plateaued, for a couple years in the late 2010s, and then it's tanked. But as I say here, a value of -1 indicates no fast ice, so a value of +1 indicates you got fast ice. So you have fast ice here hugging the coast and there. and a couple of spots there, not totally. That's a little lighter blue, so it might be in the 0.25 to zero point 0.5 range. But look here, here, almost all these coastlines. Look at all of these. There's no, according to this, there's a lack of fast ice. So if you don't have the fast ice, if you start losing the sea ice, whether it's the pack or the fast ice, what's to hold the land ice back? Answer, nothing. So now the land ice starts calving more and more, working its way up north into warmer oceanic waters and melting. The fast ice, the sea ice in general, holds the land ice of Antarctica back. You lose the sea ice, it allows for the land ice to progress, travel out, break off, and so forth. And then you toss in, I did this video some time ago, a little while ago, about how the ocean heat content is contributing to losing the cantilevered land ice in Antarctica. Okay, so going back to this, why has most research to date focused on Arctic rather than Antarctic fast ice? Number of factors have converged to give us a much better understanding of Arctic fast ice, including indigenous knowledge, more populated, right? You got people there. Fast ice has been used for transportation and hunting purposes for generations. Charting. High quality weekly ice charts in the Northern Hemisphere have been recently used to map trends in fast ice extent because there's more people in the Northern Hemisphere. Proximity. Vast tracts of Arctic fast ice are accessible from the northern coast of Greenland, Russia, Alaska, Canada, Scandinavia. Okay? It can also be found around Svalbard. By contrast, Antarctic fast ice requires expensive logistics, considerable planning for comprehensive research to take place. Yep. And that means writing expensive grants. Change. Arctic sea ice has been declining ever since the start of the modern satellite era, and likely earlier, whereas Antarctic sea ice was thought to be comparatively resilient against change until about 2015, when its variability increased. 2015, about here. What different techniques have been used to observe and measure Antarctic fast ice over the past century? The earliest accounts of Antarctic fast ice were from the heroic age of exploration, according to Wright and Priestley, based on the 1922 paper, 101 years ago. Wow. Accurately mapped the fast ice encountered on the Terra Nova expedition of 1910 to 1913, commented on the differences between smooth and rough fast ice. Nowadays, fast ice is measured both in situ and remotely. And, got some satellite imagery here, airborne photos, right? All sorts of fun stuff. In situ measurements include ice mass balance observations to determine the ways in which fast ice grows, as well as cores taken to measure the structure and chemical composition of fast ice. Remote measurements include satellite-based mapping, as well as measurements of its thickness using altimetric and other techniques. Recently, ground-based radar interferometry for monitoring fast ice dynamics was developed and used for Alaska's Arctic coast. Hasn't been deployed, implemented in Antarctica yet. And radar interferometry is a commonly used technique up here in Alaska, for the satellite data. How has remote sensing provided better data and new insights into fast ice distribution, seasonality, and thickness? Studies of the distribution of fast ice would be impossible without satellite remote sensing due to its vast scale. Until now, the most complete large scale data set of Antarctic fast ice extent has come from visible/thermal infrared satellite imagery. But this imagery is heavily cloud affected. Got a lot of cloud cover, you ain't going to see squat, and requires manual interpretation for fast ice mapping. Now, I kind of flippantly said that. It depends on the aperture, depends on the wavelength. If you can use certain setting that can penetrate through the cloud so that you can get some sort of measurements, but it could affect the accuracy or the scale. So it's a balancing act. Now, if you have no cloud cover, yeah, then you can get great data and you take advantage of it and and go to it. More recently, satellite synthetic aperture radar (SAR), very very commonly used. We use it up here in addition to the radar, uh, the ground-based radar interferometry that I mentioned earlier. SAR is used extensively up here in Alaska. It's used extensively over the planet. Has been used for fast ice mapping in both poles. SAR imagery is not affected by clouds or darkness, so is particularly suitable for this task. As we move toward automated fast ice mapping from SAR imagery, we can look forward to higher resolution, more accurate, more timely fast ice maps. Remotely determining the thickness is still a challenge. Will give you a great idea of the extent, how many square kilometers covered, but getting the thickness and therefore the volume, that's a challenge. Innovative researchers have recently been using electromagnetic induction-based techniques to measure fast ice thickness from low-flying aircraft suspending an electromagnetic induction device and flown just 15 meters above the surface. You can't do this from space. Well, 15 meters, that's some tricky flying. How is fast ice in the Antarctic expected to change by the end of the 21st century? Well, short answer, we don't know. Climate models don't yet simulate fast ice. It is hoped that within the next few years, fast ice will start to be included into many more models, giving us the ability to project fast ice extent and thickness into the future. Until then, what we can do is look at the changes in the ocean and the atmosphere projected by 2100 and make a guess. Based on this, we think fast ice will decrease in extent, thickness, and duration. Right now, we can't quantify. What are some of the unresolved questions where additional research, data, or modeling are needed? We have very limited knowledge of fast ice thickness other than in situ measurement, which are limited. As spaceborne altimeters become higher in resolution and more precise, we hope that this limitation becomes addressed soon. More research is required. Most of our current fast ice knowledge comes from smooth fast ice, but we don't know much about rough fast ice, including its thickness, storage of nutrients, role in ecosystems. The problem is most Antarctic stations are located near smooth rather than rough fast ice. So in situ measurements are difficult to achieve safely because what I mentioned earlier, rough ice is going to be tough on instrumentation. In order to more fully understand the drivers of fast ice distribution and its susceptibility to a changing climate, we need fast ice to be fully incorporated into our climate models. Without this vital tool, we cannot achieve the full understanding of Antarctic fast ice that is needed to fully assess its importance in the Earth system. And these are questions. The answers are provided by Pat Wongpan, who provided these photos, provided this graphic. Right? Fraser Wongpan et al. 2023. That's comes from their study there. So this is another aspect that needs to be considered, and we need more information and more data and more analyses to better understand what's happening. And this would be another important key aspect, key part of the puzzle as we try to get a better handle on what's happening with the climate. So, something else that we need to be looking at now is landfast ice, sea ice. We're all seeing the graphs of the rapidly dropping sea ice, but now you can think of this as another type of sea ice: pack ice, fast ice. So, hope you found this informative, and this is something we can definitely be keeping an eye on in the future. Thank you for your time.